Okay, as our final example of growth and decay, I wanted to look at Newton's law of cooling. I think it's just an interesting formula. So first we're going to define a couple of variables. T, capital T, is going to be the temperature of the object. T sub S is going to be the surrounding temperature. Okay, so what this formula does is think about having a cup of coffee or ice water or something like that. And you put it out there and you just set it on the table, it's going to slowly approach the room temperature. The greater the difference of the temperature, the faster it cools or the faster it warms. So a really hot cup of coffee in a chilly room will drop temperature really fast and then stay warm above room temperature for a much longer period of time before it finally reaches room temperature, or at least approaches room temperature. That's the idea that we have here. So dt, the change of temperature over the change in time, is proportional to not the temperature itself, but the difference of the temperature of the object and the surrounding temperature. So this doesn't look like the law of exponential law of exponential change, but we can make a substitution. Here's our inside function. So let's say y equals t minus ts. Now remember, ts, the surrounding temperature, because you put it in such a large thing, it's going to be mainly constant, relatively constant. So when we take the derivative with respect to time, we get dy dt equals dt dt minus 0, because this is a constant. So dt dt equals dy dt, so there's our substitution there. K can stay. T minus ts is y. So there we have it. dy dt equals ky. We know from the law of exponential change that becomes y equals y naught e to the kt. So we change that to use our substitution to go back to temperature. We have T minus Ts, so temperature of the object minus the surrounding temperature, equals the initial temperature. So here we have the initial value here. The initial temperature of the object minus the surrounding temperature times e to the negative kt, where little t is time. So we have a lot of variables. So temperature of the object that's changing, surrounding temperature around the object, the initial temperature of the object, again, the surrounding temperature, e to the k, which is just a constant, and t is the time that we're dealing with. So if we solve this for t, this becomes t equals ts plus t naught minus ts e to the negative kt, and that is Newton's law of cooling. So let's read this problem and we'll get started. A hard-boiled egg at 98 degrees Celsius put in a sink at 18 degrees Celsius. Okay. After 5 minutes, the egg's temperature is 38 degrees. Assuming that the water is not warmed appreciably, so we haven't warmed up the water by putting the egg in there, how much longer will it take the egg to reach 20 degrees? So let's write down some given. We have our initial value, initial temperature of the egg is 98 degrees. The surrounding temperature is the water, which is 18 degrees Celsius. Let's write down our other ordered pairs. Let's see, time and temp. So we have our independent and dependent variable. That's little t to big T. That's 5 to 38. We're going to use this to find K. So let's plug in what we have. In 5 minutes, it's going to be 38 degrees. And that equals 18 for the surrounding temperature plus the initial temperature minus the surrounding temperature, e to the negative k times 5 minutes. Okay, we do our solving, we subtract 18, divide by, that's 80 there. Take the natural log, divide by -5. And we would get that k equals, let me look here in my notes, 0.277. Okay, so we have our next point. We want to know when it reaches, we're looking for time when it reaches 20 degrees. So when it reaches 20 degrees, we still have our surrounding temperature plus our initial temperature minus the surrounding temperature, e to the negative 0.277 t, because we're looking for how long. So again, we solve all this. I'm going to trust that y'all can do that. We subtract 18, we get 2. We're going to divide that by 80. Take the natural log, divide by negative 0.277. That comes out to be about 13.3 minutes. Now, just like in anything, we need to make sure we answer the question. So even on a problem like this, we got to make sure we answer the question. This seems legit, but the question is asking, how much longer will it take it to reach 20 degrees? Well, we were already at 5 minutes. So 13.3 minus 5 minutes is 8.3 minutes. So that's how you work with Newton's law of cooling. It's just an interesting, the substitution is an interesting way to get to the law of exponential change so that we can solve it very, very quickly.